I'd like to start off with a bit of the context to this. UK government is bound legally to climate targets, and it set in 2019 the requirement to get to net zero by 2050. And there are a variety of other targets that have been set by the Committee on Climate Change for 2030, 2032, 2036. Since 2019, the government has issued 3 papers at least, running to some 450 pages. And these documents are quite impressive, 10-point plan and so on, but they are very high on aspiration. They've got lots of impressive targets, but they don't have very much in the way of a credible route to get to net zero, or what net zero and the steps there are going to look like. In July this year, the High Court ruled that the strategy for getting to net zero by the government is inadequate and unlawful. And last month, the government acknowledged that that was the case. So we're in a bit of a bind in that respect. My background is in power engineering and electrical distribution systems, and I've been looking at energy for quite a long time. And what I would like to do is offer to you a suggestion of how we might migrate from where we are at the moment to lower carbon and ultimately net zero. And what I would like to do is quickly go through the whole business of climate and energy, because the whole climate change thing is brought about by energy, yet our whole society and the population of the planet rely on energy. 83% of our emissions worldwide come from fossil fuels, from oil, gas, coal, and only a small amount from nuclear, hydro, and wind. And it's rising. So you see it continuing up, and all those relate to emissions. And the result of that is annual CO2 emissions. Now, this is the last century, and you can see they're rising from virtually nothing to 42,000 million tons a year of carbon dioxide being put into the atmosphere. And that is then resulting in a rise in the CO2 levels from about 280 parts per million in the atmosphere up to currently 420 parts per million and rising. And this is instantaneous within the context of geological time. Never in the last million years has CO2 levels in the atmosphere been above 300 parts per million. Just to sort of look at where is it? What are we messing with? That's the atmosphere. That is the incredibly delicate, thin membrane that prevents our planet from becoming like the surface of the moon. It's just salutary to look at that. The result of the carbon dioxide CO2 level rise in parts per million is the rise in the mean average temperature of the planet. And it's risen 1.1 degrees since pre-industrial times, and it's continuing to rise. But it's not uniform. It doesn't seem very much, 1.1 degrees, but it's at the poles. For example, down here on this diagram, the bottom left, December, January, February, the northern poles are rising by 5, 6, 7 degrees, and that is causing huge melting. It's causing increases in desertification in various already stressed areas. But the most frightening thing really is the tipping points. These are positive feedback systems whereby a perturbation on a natural system leads to that system moving in such a way that it increases the perturbation. So it's a self-reinforcing cycle and leads to changes that are faster and faster and irreversible until it reaches some alternative state, like the whole of the ice caps have melted and the sea level has risen by 60 meters or whatever it is. So polar ice caps melting, Greenland melting, it opens up sea, it increases the radiation absorption from the sun, the temperature rises, you get more melting. And the same applies to permafrost melting, rainforest desertification, and even the Gulf Stream moving. One of the most frightening statistics I find, and I've checked it several times because I didn't believe it, Greenland is losing ice at an average of 1 million tons a minute. 1 million tons a minute. And yeah, it seems unreasonable. So what are we doing about it? Well, the IPCC on its 2018 report said we have to try and keep below 1.5 degrees centigrade rise. And in order to do so, we've only got 66% chance of doing so if we can limit our CO2 emissions. That is forever to 570 gigatons. And that was from 2018. And yet currently we're emitting 42 gigatons per year. And we have to cut this emissions down uniformly right through to 2050. It's no good waiting until 2040 and then doing something. But, oh yes, and this was an interesting graph. This one shows what we're actually achieving. So this is the trajectory over the next 100 years of what we have to do to keep within 1.5 degrees. That's within 2 degrees. This is what countries are actually committing to. This is where the current projections are. So we're absolutely nowhere near getting where we have to. But the reason we've got in this mess is because we've had very large quantities of low-cost energy available, and that's allowed us as a species to multiply. I think it was last Tuesday, was it? We were 8 billion or something? And
2.5 when I was born.
2.5, was it really? Gracious me. And it's allowed us to have an increasing standard of living, so-called, or standard of consumption. And that profligate buy it, throw away, get another one, scrap it, and even recycling is just becoming untenable. But it's all being powered by excess energy. But we can't switch it off. We're now 8 billion people, and we can't change the standard of living beyond a certain point without the whole system falling apart. So we still need energy. We need it for heating, cooling, cooking, everything, including creating the new infrastructure for a low-carbon world that we have to get to. So now I'd like to look at UK energy. And the start point for that is information provided by BEIS, the government, in their so-called Duke's statistical table, and next please, and a very interesting diagram that comes out each year, which is an energy flow diagram. Now, I'm not going to go through all that in detail, but I've got a simpler one coming up next. What I would like to point out to you is the principle of this diagram. It's really worth getting hold of this one and looking at it if you're interested in such things. The thickness of the line represents the energy flow. Energy is, in terms of fuel, is coming in at the left-hand side, and the consumption of where it's going is on the right-hand side there. And just at this level, because it's the government's official figures, I'd like to draw your attention. This is oil and its derivative products, petrol, diesel, kerosene. This is natural gas. And you see the size of those. This is wind and solar, the bright pink, bright red one here. This is nuclear, the pink one, and that's biofuel, of which a large proportion is actually being shipped across from North America and fed into Drax Power Station in an entirely unsustainable, unaccountable manner. So now, just a simpler version to work on. Oil, petrol, diesel, and the rest of it, mainly used in transport, also used for heating. Gas, the majority is again used for space heating, domestic, commercial, but quite a lot of it is fed into electricity generation, combined cycle gas steam turbine plants. And wind and solar is a relatively small amount. It's 80 terawatt hours a year electrical. It's slight mixed units. This is electrical, so it's slightly more valuable because it's a higher grade energy. Nuclear 150, and then biofuels, and I say Drax there, and then heating this in this direction. And we're using about 300 terawatt hours a year of electricity. So that's our start point. What I would like to point out is where we've come from. And it's not that the history matters, but what matters is the way in which the history is being used to suggest that everything is fine, chaps, don't worry. So oil is much the same since 1990, which is the sort of baseline that a lot of energy statistics are taken from. Coal has dropped to virtually zero, and gas has increased in replacing that. Solar, hydro, wind has risen, but it's wind. It's wind power. And I pushed this one up a bit to reflect that it's higher grade energy. Nuclear is about the same, and of course there's a big increase in biomass. One of the things that I believe is causing a lot of difficulty is that the government, every time you write to an MP and say, I'm really worried about climate and we should be doing more, you get a reply that said, we are very proud to say that the United Kingdom is leading the world in the charge against climate change. We have reduced our CO2 emissions by 48% since 1990, at the same time as increasing economic output by 75%. Now, this is, well, it's basically wrong. And it's used to sort of give everybody the impression everything's fine and the government's got it under control. The 48% is based upon domestic emissions. It does not take into account the fact that back in 1990, we had a big industrial base. We could make everything from reactors, steam turbines, and all the appliances. All that has either gone to France, sadly, in the case of steam turbines and locomotives, but mainly to the Far East. And so the emissions associated, the large emissions associated with that, have all gone offshore. And we are now importing all those things, and including quite a lot of food. If you take the consumption emissions into account, and you take into account the emissions being given out by other nations in producing goods for us, then it's only a 22% reduction. Now, the 22% reduction is an actual reduction in practice, but it's suggested this shows we're on course. Well, it did in the past, but it isn't now, because it's based upon the reduction in our use of coal. And coal, if you go over the last century, it's going to be enormous, but it's now zero. Natural gas, the dash for gas came in the 1980s, 90s, and that is now where we are. The thing about gas compared with coal is that natural gas, NH4, 4 hydrogen atoms and 1 carbon, and coal is carbon. So you get more energy out for the same amount of CO2 emissions. The other thing with gas is that you can convert it to electricity or use it for heating at a much higher efficiency level than you can or could with coal. And that's what accounts for the 22% reduction. So what I'd like to look now is at energy transitions. This is the same diagram again, but what I wanted to draw to your attention is heating and transport are some of the biggest emitters of CO2. And the problem is it's emitted at site. It's emitted at the place, it's on the tailpipe of a car or your central heating boiler output. And if we're to try and reduce CO2 emissions, we have to either change those fuels completely and to do so, essentially, we have to try to turn it as much as we can into electricity use. And what we can't do, substitute synthetic fuels, biofuels, or hydrogen. So what I've been trying to do is forgive the complexity there, I'll just summarize it, but what I've been looking at is taking all the different utilizations of energy and saying for each one, what could we move it to? How could we change it? How could we economize? And what I've ended up with on the two left-hand columns here, this is the amount of fossil fuel that we use at the moment, which is 1,300 terawatt hours a year and about 300 terawatt hours of electricity. If we try to move as much as we can to electricity without changing our consumption habits, then I believe we can do that by tripling our electricity supply, and we would drop our liquid fuels, which might be substitutes with hydrogen or biofuels, by about 63% down to 490 terawatt hours a year. But in parallel with that, I believe we also have to make savings. We have to insulate homes better. We have to manage energy better. We have to drive slower, transport heavy goods and so on onto rail, and use public transport. These sort of things. I've worked on roughly a 30% reduction in consumption use, and if we did that, I believe we could get away with about doubling of the electricity consumption and drop our emissions, liquid fuels, by 77%. And of course, those ones, if we can turn those into lower emission fuels. So in summary, what I'm suggesting is transfer 70% of our energy use to electricity. The remaining 30% would have to come from synthetic liquid fuels and apply energy savings of, if you average it all out, about 30%. And that would change our diagram like this. What we would end up with is inputs, nuclear base load. I've assumed that Hinkley C will someday get finished, and maybe we'll have Sizewell C on top of it. Wind and solar, we would increase by a factor of 4 times, which is, I think, roughly where it's heading. Gas would stay the same, it turns out, but the majority would be used for electricity generation, and it's needed there because the wind and solar and hydro are all variable, unreliable, and have to be covered by the fast-moving gas power station generator. I assume that some gas will be used for a hydrogen grid through cracking blue hydrogen, and spare wind energy used by electrolysis for green hydrogen. And these would be used both for feeding to places that you can't put electric heat pumps or you can't use electric vehicles, to produce synthetic fuels, aviation, shipping, and the residual heating. And we would end up producing twice the amount or using twice the amount of electricity. So we would have centralized emitters of CO2. And then the question is, can we take that 150 megatons that we would be emitting, and how much of it could we sequester? And that's where I was asking my cousin Eric at the back, who is an expert on carbon utilization, capture and storage. And I think his view was, well, you're pushing the boat out a bit on 150 megatons, but we might get some significant direct way in that direction. And he's pointed to me to the Schlitner gas field, where the Norwegians have been sequestering 1 million tons of carbon dioxide per year for the last 20 years. And I think there's an Australian one, isn't there, with 4 million tons a year. So the technology is sort of taking off, but it's also to do with incentive and pressure to cover that. Now, this is assuming wind is 4 times as much. Part of the problem with the debate about greening our energy is people say, well, we'll just build lots more sustainable power stations. We've got, before very long, every home in Britain will be totally powered by wind. Well, the problem is the wind doesn't always blow. The blue line here at the bottom is the wind generation on a day basis, and that's on a monthly basis. And the red line is the compensating gas burning in combined cycle plant to fill the holes when the wind isn't blowing. And you can see that this was just happened to take it in May, April, May, a couple of weeks with very little wind. And if you look at here, there's June, July, September, no wind, but also in December, there's quite long periods, certainly hours, days, weeks, sometimes even months with no wind. And we have to do something about that. We have to sort of understand all the time when you have electricity, the generation must exactly match the consumption. We switch on a light switch, a generator somewhere has to produce a little more electricity. There is no energy storage in the grid. The only way we can store electrical energy is converting it to something else, store it, bring it, and convert it back again. So hydro, yeah, it's very useful, but it's only a matter of hours and only part of the grid consumption anyway. Batteries, even if you strap all these electric cars together, 1 million electric cars, if you could even connect them all and allow the owners to put it all in, it only takes you for half an hour on the grid. Synthetic fuels, yes, but we should be using them for transport, and hydrogen, yes, but how do we store it? You can't liquefy it, you have to compress it. So if you take your excess solar wind and you convert it to hydrogen through electrolysis, for example, you end up with 75 units from 100 of heat energy in that hydrogen. You put it through some sort of gas storage like giant salt mines, and you compress it all down there, and you decompress it, and you bring it back, and it's 65 units of heat, convert it to electricity, and you come out with 33 units of electricity. So you're round the loop efficiency is just 33%. It's obvious that we need something more reliable and we need more. So what I'm looking now at is what's the next step? How do you get rid of the need for gas? So what I'm assuming in the longer term is, yes, we've already increased our wind capacity by 4 times. We've doubled the conventional generation 3 nuclear capacity. We're using smart grid, that is demand side management, as much as possible to even things out. But my personal belief, and it's controversial in a way, I believe the only way we're going to go forward, and it will be forced upon us, is small modular reactors. And these things have to be intrinsically safe. They can't rely on complex safety systems and control systems. They have to be factory built so they can be mass produced. Fast breeder type, which means that they work with fast neutrons and they can use a much wider variety of fuels. Waste consuming, so they take the previous generation's nuclear waste and reutilize that, because the previous generation only burns off a very small proportion of the energy there. Hopefully, combined heat and power, so you can use it for district heating, because it will be intrinsically safe, and you can therefore put it into urban areas, and some of them hydrogen producing. So this is my vision for the future. So as before, you've got your 3rd generation, 300 terawatts hours a year from conventional nuclear, you've got the wind, but down here, I'm suggesting you have a whole rollout distributed across the country at load centres of small modular reactors. And I just did one calculation, said if they were working at 40% load factor, that is, if you go up and down in order to compensate for wind and for changing load requirements in winter and summer, then you'd need 200 reactors at 250 megawatts each at 40% load factor. And you'd dot them right across the country. They would be in urban areas, produce local hydrogen supply, and local electricity generation would go into the grid. But the waste thermodynamic heat that comes from it, could be used for district heating schemes. They're small enough that they can be used for ships propulsion, and they would also be located where you have high energy use industry. And one of the things I've done in trying to make assumptions on how much energy we need, I've assumed that we're actually increasing quite considerably our industrial base. We're onshoring quite a lot of what we do and reducing the level of dependence externally and our own dependence on imported goods. So that vision depends on nuclear. And so I'd like to just say a few words about nuclear power. Just quickly, the advanced gas-cooled reactors is what we've centered on in this country. They've been very successful. They use mediumly high pressure carbon dioxide as the coolant, which means quite complicated but doable pressure containment vessels, concrete and steel. And they've been very effective. 45 years they've been running, and they're gradually coming to the end of their lives. The rest of the world went for pressurized water reactors. And that was because at the time when we were building AGRs, pressurized water reactors were a lot cheaper. But they use water cooling, and to keep the water liquid, they have to operate at very high pressure with reactor vessels 6-inch thick, very specialist designs. And nowadays, they're very much more expensive because you have all these extra safety systems and pressure domes and the rest of it. I believe the next generation is small modular reactors, as I said before, and I have a particular interest, just having looked at a variety of them, in molten salt reactors. So just a word about molten salt. The idea, and again, you might want to sort of I can send you the slides if you want the detail, but essentially they are intrinsically safe, otherwise known as walk-away safe. If the grid connection disappears, if nobody's taking any energy, everybody's run away, they just sit there at temperature but not producing any heat. And it doesn't need any active power to drive its safety systems. It's intrinsic in the physics of them. Secondly, it is able to dissipate the residual heat which comes when you shut a nuclear reactor down. The reaction doesn't stop completely. So you've got a certain amount of heat you have to get rid of. Thus, Fukushima, that's the problem there. So it doesn't require special cooling systems. It doesn't require electricity or pumps. And another thing is the fuel in this type of reactor is mixed in salt, and the nature of it is such that it can't be used for military purposes, which at least helps for anti-proliferation. Wide range of fuels, I've mentioned before, can use depleted uranium-238, it can use plutonium, use thorium, different types of reactors, but high temperatures. And again, that's quite important. Typically working at 700-800 degrees centigrade compared with 325 for a pressurized water reactor gives you twice the efficiency of thermodynamic conversion to electricity. And that is important because many places there's water shortage. And the way a power station works, the heat energy has to eventually be taken away. And it comes out at sort of 80-90 degrees centigrade. And power stations by the sea use seawater, but others use water which feeds into cooling towers. So all the steam coming out of cooling towers is that. If it's twice the efficiency that you get out of it, you have half the water requirements for the same amount of electrical energy. And that is really important in some areas. Fast modulating, it's got to go up and down. Low cost, I'll come to that in a moment. And faster delivery because it's manufacturing. And my view is this is where the shipbuilding industry and the oil and gas industry can come in because these things operate at atmospheric pressure because the liquid salt stays liquid right through to 1400 degrees centigrade. So it doesn't require high pressure. It doesn't require huge containment domes. It's using straightforward piping, pressure vessels, pumps, which is the bread and butter of the shipbuilding and the oil and gas industry. And it's where I believe they have to go. But the problem is licensing because it's nuclear and that's a long process. But again, we managed to turn vaccine licensing round to a few months from several years, and we'll probably have to do the same with this. Cost. This was produced by Moltex, which is a manufacturer, designer of molten salt reactors. From 1970 through to now, PWRs pre-Chernobyl were relatively cheap. This is levelized to, I think it's 2014 prices. It's the overnight capital cost. And a Chernobyl accident was there, but already safety requirements were rising, Fukushima accident there, and that's the sort of price per kilowatt hour for capital cost for Hinkley C. What they're saying is that they can come in at this sort of level. These are two different. One of them is actually a large turbine on a small reactor, because it gives you greater efficiency and lower risk, and it's quite an ingenious design. The other thing that upsets people or worries them very much, quite reasonably, is nuclear waste. But most of the waste that is in Sellafield, and Sellafield is military nuclear waste, much of which has been extremely badly managed. Modern reactors, the waste is kept, well, first of all, far less of it, and it's kept on site, and it's priced in, and it's all designed in from the outset, along with the decommissioning costs. Sellafield site itself is 260 hectares, which I find it's not very much. It's double the size of the average farm where I come from. It's tiny. And the material is contained there. We know where it is. And you have to take this as a risk analysis. What are the risks we're facing? So the risks from nuclear waste are ionizing radiation, alpha, beta, gamma particles, neutrons, which we've been living with for the last million years ever since we evolved. In comparison, we're putting out 40 gigatons a year of carbon dioxide, 500 megatons a year of methane into the atmosphere, 300 megatons a year of plastic, and so on. And we're also facing an existential threat through climate change. So you weigh one against the other, and to my mind, it's a no-brainer. This, I thought, was an interesting slide. This is to produce our world in data. This is the number of deaths per unit of terawatt hour of energy produced. So the thin line there is nuclear, and that's biomass, natural oil, gas, sort of 100 times more dangerous, the number of people killed as a result of it. And incidentally, this one is the greenhouse gas emissions over the lifetime of the plant per gigawatt hour produced. And again, it's way down, 3 tons. And interestingly, it's actually less than you get from wind turbines and even less than you get from solar. So notwithstanding all the things about high capital costs of nuclear plant, it's not all that bad. So finally, my view is decarbonisation can be done. It needs vision. It needs a picture. People need something to look at and say, yes, that's where we can get to, and I'm prepared to sort of go and work to try and get it there. It needs courage, commitment, but above all, it does require the government to tell the truth, where we are and what we haven't done, rather than keep spinning the story about 48% reduction, don't worry. It needs strong leadership. It needs legislation, because sadly, a lot of industry is not going to move until it's forced to do so. So it needs legislation and incentives. And individuals can make a saving. There's lots of things we can do, but ultimately it's pressurizing the government to move. And on the personal front, one of the things that I find is very interesting, I didn't mention here, is TEQs, tradable energy quotas, where everybody is issued with a certain quota of energy and they can trade them, and it will start to put a much stronger pressure in for people to economize and to work out how to go forward. TEQs, I think, is an interesting thing. And then people changing their diet, changing their travel patterns and things like that. The United Nations Secretary General said, we are on a highway to climate hell with our foot still on the accelerator. But we can turn it round, I believe. Thank you.
That was absolutely fantastic, John. You covered such an enormous breadth of information very coherently. It raises lots of questions. And if I may just start with one, to understand in terms of your plan, how far it differs from the current net zero strategy of the government. Because clearly small nuclear reactors have been part of what is discussed at a very high level. What you're talking, but it also talks about all the other things you mentioned, CCUS, hydrogen, wind power, solar, and so on. How big a shift are you looking at in what you're proposing?
The true answer is I don't know. What the government papers say is that we look to do this, we're looking to invest in this, and then it's got sort of pictures of people enjoying this, whatever it is.
Yeah.
But it hasn't got, as far as I've found, any plan that says by such and such a date we are going to produce that many terawatt hours per year from this, and we're going to move that to there and that. Yeah. And so it's not that I'm completely dissing the government's plans. It's that it has to be much more specific, and it has to give industry and commerce a clear steer of where we have to go to. Where are we going to put our money? There's lots of money out there looking for sustainable places to invest. If we have a strategy, that's where we've got to get to, and these are the steps to get there, then people can move. So I don't really know the answer to your question, because I haven't yet been able to.
No, that's fair, because a lot of these things are thus far at a very, very high level. Some things, the low-hanging fruit of moving away from coal is obviously
that was
plucked. But and secondly, just generally on the technology, I mean, one of the concerns one has, 2030 has become an incredibly important target in terms of 1.5 degrees centigrade above pre-industrial levels. And all of these proposals, but particularly in relation to nuclear, there's a lot of new technology. Do you think we can get, you mentioned licensing.
What new technology? It's very easy for pundits to say, we will build lots more sustainable power stations. We'll use new technology for this. What is this new technology? Yeah. You really have to go back to the fundamental physics. Say, what energy resources do we have? Well, we can burn fuels by oxidization, or we can use nuclear, and we can harness the secondary things like wind or wave or tidal and so on. But it's a pretty limited range. And you have to really get down to the science of it and say, what possibilities have we got? And my view is you're just out of the league other than in nuclear, because we don't have very long. I mean, it's a moment in time, and we've got to get this fixed. people talk about tidal, and there's these tidal race turbines up in the where is it? North of Scotland.
Yes, the
Pentland Firth. And they're lovely and they're wonderfully impressive, and they're all of 1.5 megawatts or something with a 20% load factor. And, and everybody runs wild about it, but it's not getting us anywhere. Tidal barrages, yeah, but how much energy are you putting in to put the barrage? And yes, huge quantity of water. It's only going up and down that much compared with what.
But do you think these small modular reactors can be brought online and financed, which requires people to feel comfortable about the technology, fast enough to deliver?
Yes, I think so. But again, it comes down to whether we have. It's a hackneyed thing. We're in a wartime situation insofar as we've got a climate crisis rolling up to us with tipping points about to fall over. We have to do something.
Yeah.
And if we really wanted to go ahead, and if not just me, but the powers that be and all the other pundits said, yes, that's the way we have to go, I believe we can get there in 10 years.
Lovely. Listen, I'm going to throw it open to the audience for questions.
In your graph, the relative cost of building different sorts of power stations, already investing in small nuclear reactors.
I think they are a bit, but they're terrified of two things. One, the general public fear of nuclear. The word nuclear frightens. And it's not unreasonable. I mean, nuclear is, in most people's minds, a nuclear bomb. The understanding of why a nuclear power station is nothing like and can never be a nuclear bomb is too detailed for people. So that's one thing. But the other thing is Angela Merkel. The German nuclear program was all being built up. And then Angela Merkel, when was it, in 2000 or so, made an alliance with the Green Party on the basis, we'll stay in power, but I agree to shut down all nuclear. So suddenly you have this immense stranded assets. There are lots of companies who had invested in nuclear, and all the cost is up front in building, is the capital cost. Yeah. And suddenly they were left with a whole lot of nuclear power stations. They're just about to start them up, and they said, no, not allowed anymore. And that sent such a shock through the industry that everybody sort of ran a mile. And what used to be an 8% investment return rate, which the market was happy with, suddenly goes way up because people say, I want my money back in 3 or 4 years. You never know what politicians are going to do.
That's a very good point.
And shut it down. So that, I think, is what's holding people back. Modular reactors are potentially much, much cheaper. They're a much simpler technology, and the investment, I think, is much less. So Hinkley C is some phenomenal cost because you're building a power station of 3.2 gigawatts. These small nuclear reactors, they're typically 100 megawatts, 500 megawatts, that sort of size. And they use standard components. Because they're high temperature, they can use the standard steam turbines that are being rolled out by China. There are hundreds for coal-fired stations and the rest of it. It's a much more comfortable technology to invest in and potentially lower risk. Yes, with the salt pool, the problem is actually corrosion of pipes. But I think I'm led to believe that there are workable solutions for the.
But you can create, you think, a competitive market, which is what's been absent before.
Yeah. So thank you. That was a really interesting talk. Going back to the question of safety, you said that these sorts of nuclear reactors are nothing like this. People don't understand that. The explanation for why that is. Well, for me, that's absolutely critical, getting public support behind it. So yes. My question is in two parts. First, would you be able to just try and explain to the layman like me why there's no risk of these things being like bombs? And secondly, even if they're not like bombs, why are there no real risks associated? I think about things like Chernobyl or something like that. That's what those are the images that come to people's minds. So those were non-engineered.
No, that's absolutely the centre point of the concerns. The reason why it's not a nuclear bomb is because a nuclear reactor involves a chain reaction. That is, the neutrons that are fissioned by one atomic action have to lead to enough neutrons being released that it will lead to another fission, which also produces energy, which leads to another one. And that the reproduction cycle of that is rather like the COVID rates, which we've all been talked about as 1.1, 1.2. The reactivity of a nuclear reactor is about 1.001 or something like that. It's just above unity. So it can very slowly increase its reactivity or decrease. The nuclear bomb, on the other hand, is made such that the reactivity increase rate goes up faster than the atmosphere, the sound can contain it. So it produces a huge sphere of compression, and that's the bomb. But it's the physics of it is 1,000 miles from the physics of a nuclear reactor. And a nuclear reactor is designed never to have a reactivity increment rate more than a very very small amount. So that's fundamentally why it's different. Sorry, if I could just finish. The other points you're making is Fukushima and Chernobyl. Chernobyl and 3 Mile Island were pressurized water. Well, it was actually RMBK, RBMK reactor, the Russian one. But they're essentially water cooled. The RMBK reactor was fundamentally unstable, is by design fundamentally unstable. I can explain afterwards, say why. But anyway, that was grossly mishandled by a bunch of engineers who knew nothing about nuclear, who came from Moscow with authority to go and stuff around with it. And it ended up with the containment being burst in a steam explosion. It wasn't a nuclear explosion, steam explosion. But it led to a fire in the graphite moderator, which then melted fuel, and lots of radioactive material was spread into the atmosphere. It was terrible. Since then, of course, all the PWRs, which is why the cost has gone up, have now got to have huge pressure domes over the top of the pressure vessel, so that even if the pressure vessel burst or the heat exchangers or pressurizer burst, the steam could still be contained within this reinforced dome over the top. Modular reactors, salt-cooled modular reactors, work at atmospheric pressure. Because the coolant and the fuel is mixed, because the coolant does not evaporate until 1400 degrees centigrade or something like that, they don't need to be pressurized. So you have much simpler controls.
John,
yes.
I'm conscious that there are others outside. I think we should have that last question, and then we should let them in 2 minutes.